list of presentations. So it is a CHEM676 computational chemistry, and as a part of this class, we are learning both theoretical background and practical skills, which are listed on the bottom line. And since the class is big and we have some schedule conflicts, we chop the presentations on 2 sections. So everyone in yellow presents today, everyone in cyan presents tomorrow. The skills are covering usage of WASP software, which is very efficient and comfortable for describing solids and materials. And we didn't have volunteers, and we didn't show in the labs the questions 4 and 5, but I will try to blend them into the coming lab when we will start projects. The 4 is needed for periodic solids, 5 is needed for more exact, more precise band gap energies. So the whole story, all set of presentations is a one chapter that we all should either listen now or watching the recordings. And let's go through starting from the presenter number 1. So Rizvi, please consider to share screen. I'll stop sharing. And all presenters, stop sharing. All presenters are invited to spend 5 minutes on presenting and then answering questions. So questions are very welcome, noticed, and credited. While speaking, please enable both microphone and camera if available. Okay, I believe Rizvi is starting.
Yeah, can you all see my screen?
I can.
Okay, let's start this. Hi everyone. Today I am going to present on the goals and abilities of DFT and the preparation of the input file for the WASP. Starting with the goals and abilities of the DFT theory. Basically, DFT theory is the theory we use to find the electronic structure of atoms, molecules, and solids. It also gives us the quantitative understanding of the material properties, such as the optical properties, heat and geometrical optimization, as we did in our lab. The basic goal of this theory is that it gives us the more accurate result as compared to other theories, such as the Hartree-Fock theory. Then comes the abilities of the DFT theories. Instead of many body wave functions, we can consider one body density in the DFT theory. It can directly bypass the direct calculation of many electron wave functions, and it can also be used for the large systems. Nowadays, semiconductors, to find the electronic structure of semiconductors, this theory is commonly used. Then comes the input file for the WASP. We already know there are 4 input file for the WASP, like postcard, incard, K-points, and podcasts. Postcard is basically the position of the geometry, the box which contains the atoms and the electrons. Basically, these are the coordinates of that box, which we give in the postcard. And postcard come from the position or position word. For this, we follow the set of commands, such as these, the sort, in which we convert our TIO4.xyz file into postcard, and then we can edit this postcard file as per our requirement. And we just rotate this to angle of 0, 0, 0. It is the requirement for the job summation. And then we convert the file with the basically coordinate 666. These coordinate is just to create a vacuum around our box, so that we can avoid the interaction with other atoms. Then comes the input file. This is the file in which basically we did our job. We do what we want to do in this file. And as we know, we did the geometry optimization and heat jobs in the labs. Then comes the command for the in-car file. Basically, we just copy the in-car input file from our binary database, and then we can edit the file because it contains the number of steps to a large number of steps. We can reduce the number of steps to 0 to avoid the time submission of the job, to reduce basically the time submission of the job. Then comes the K-points file. This is basically the information of the reciprocal space lattice vector. We normally taken this as 111, and the velocity of this vector is taken as 000 because we don't want to move this vector. Then comes the podcast file. This file is basically contains the effective core potential information. It contains all the information of the element potential present, and we can see the behavior of electron in this file. To produce this file, we basically use this set of commands in which we can copy our required element, and then we can follow the command grep podcast to submit the file job submission. And this file pop-up which contains the information of the elements we selected, such as the titanium, oxygen, and hydrogen. Then after producing these 4 files, we can finally run the WASP. And for running the WASP, we use the command bin binary WASP, and we run this command on Photon server. And when we run this command, there are several set of files produced, which unfortunately I didn't edit in the presentation, but I can tell it orally that the files are wavecar, outcar, charge file, and etc. We also work on this file in our lab. So this is all from my side. Thank you so much, guys, for listening.
Okay, please join me in thanking Rizvi. And presentation is open for discussion. So any questions from online? Okay, I see there is a typed question from Haley. Would you like to verbalize your question, or ask Rizvi to read it out loud?
Yeah, how do you know what size to define the box?
Actually, the box is basically the size of it. It is the size of the atom, and we select it anonymously, I think.
Anyone wants to criticize or correct this answer? Any different opinions?
I think it is based on coordinates. We can see the coordinates, and based on that, we put the sizes.
Okay, yeah, thank you for the discussion. Any other questions to Rizvi? I do have a couple. So Haley almost took my question number 1, which I really appreciate. But in your think to WASP command, what do you expect? What would happen if one would use numbers different than 666? If you take it bigger or smaller, just philosophically or from the common sense, what would happen if you replace the 666 to 555 or 777, or just explain how you, what do you think about these parameters?
Basically, these parameters are the vacuum we produce around the box we selected in our file. If we increase the parameters, the size of the box, which we used to say that it is the vacuum around the box, it will increase.
Okay, and how would it change electronic structure? Will the gap increase or decrease? Will there be like which consequences?
Gap will increase, I guess.
Huh?
Gap will increase, I guess. I'm not sure, but I guess so.
And if one takes like about 2 to 2, what would happen naturally?
It should be reduced.
Yeah, very small, not 0, but
Yeah.
about 2. Would you agree that it will correspond to formation of chemical bonds across between the neighbor molecules? Chemical bonds between neighbor molecules.
Yes.
Okay, good. Thank you. And what would you do if the model takes too long to converge?
Yeah, I will reduce the number of steps. So,
okay.
Yeah.
Would you try it on a different computer rather than Photon?
Yeah, we tried on NSRC.
Okay, good. Yeah, thank you. And the last one, what do you do if you do not believe the instructor?
What?
What do you do if you do not believe the instructor? Like if the templates, if you are not comfortable with the templates of the in-car, which website one can look through to design in-cars independently?
Okay, I don't understand the question actually.
Like if you do not like how the in-car files are formulated.
Okay.
If you want to wipe it off and create it from scratch, where would you get a help?
Yeah, I can edit the in-car file.
But if you want to write it from the beginning, fill all parameters, which parameters and their values, where would you get help?
Ting to WASP?
No. In-car. Did you found any website? It's a question to everyone. Did you guys found the website that gives templates of the in-car or explain each keyword?
Yeah, I think you are talking about the CubeGen.
The Haley is answering in the chat line.
Okay.
So if you type in the Google in-car space WASP, enter, it will give you a lot of teaching materials.
All right.
Or if you select any keyword from the in-car, like Ibrion, WASP, enter. It will give you to a
it will give.
And Haley provides here the link to it. Okay, please join me thanking Rizvi for very important talk and giving us an overview how to start. So the next presenter is Venjan. So Rizvi, you're welcome to stop sharing.
Okay.
And Venjan is welcome to start sharing.
Hello everyone. Today my topic is WASP output and visualization of orbitals. There are some main output fields and the other fields among the WASP field list, and the main output fields including outcar, OSC car, count car, exit car, DOS car, charge car, and wave car. And next, I will introduce you some detailed information about each kind of output fields. Outcar field gives detailed output of VSP ROM. It including the summary of the used input parameters, information about the electronic steps, stress tensors, forces, local charges, and magnetic moments, and dielectronic properties. For the OSC car, it's the information about the convergence speed and about the current step, including the chosen self-consistent field algorithm, convergence of the total energy, charge and spin densities, free energies, magnetic moments of the cell. And for the count car, it's the information needed as an input for the next molecular dynamics job, including the lattice parameter, previous matrix, ionic positions, and optionally velocities. The format of the count car fields is the same as of the postcard field. Hence, it can be used directly for continuation runs after having opened coupled to the postcard field. And for the exit car, it's updated ionic positions of each ionic step. DOS car including the total and integrated DOS and optionally the local particle DOS. Charge car including the lattice vectors, atomic coordinates, and total charge density multiplied by the volume. Wave car including the information of wave function coefficients of the orbitals. After we got this output fields, we can visualize the orbitals. But before that, we need to generate some fields we needed to visualize. Firstly, make new directory and copy the output field count card as a new postcard, and copy this a list of series files to the new directory and modify the values in car as shown in the figure. And then we run the dispatch command. We can get these two fields. After that, we need to transfer the postcard and the file we generated to the local computer. Open the VMD software and load the postcard file into the VMD, and then we choose graphics representations to create a new representation. And the drawing methods, we choose the dynamic bonds to show the dynamic bonds figure. And then also in this VMD software, we load another files we generated and choose the correct file type. This time we drawing the solid surface using isosurface method, and then we can see we got the visualization of the orbitals. And that's all. That's my presentation. If you have questions, please feel free to ask.
Okay, please join me in thanking Wenjian. So the presentation is open for discussion. Other questions in online? Let's check the chat line. Okay, I do have a question on my side. Wenjian, you did. Thank you. It's a great talk, and it gives like first talk was on the input, how to start, and second, how to analyze. They already create a minimal set to do research, but among the output files, you did mention DOS car, and we in the lab were doing DOS by some other commands. So just what is your expectation and opinion? Are they the same? Are they different? Why we did it different way? Is the DOS car naturally provided by VASP give any benefits? Just your expectation, or maybe if you read or tried to look into this file, what do you think?
Can you repeat your question? I didn't understand it.
So your first you mentioned X.car, second DOS car.
Yes.
How the content of the DOS car differs or agrees with density of states that we plotted in our homework?
I think it should be the X.car contains the
not exact DOS car, just DOS car. Let's discuss DOS car.
Okay. For the DOS car, I have no idea.
Okay, that's fine. I'll give a comment for the speakers of tomorrow and for the presentations at the end of the semester. The idea is the presenter reports only his or her experience of running programs and getting output. The general information from web is something that all of us can read. So please report only things that you tried yourself and you can explain. If you are not sure, just remove it from the presentation so you do not provoke questions. So the DOS-CAR would work if you use much more K points and if you have bigger systems. The method for making density of state that we used in the lab will work for very small molecules and for big as well. We provide Gaussian profile for each line. In the DOS-CAR, this procedure of assigning Gaussian profile is missed. They use literal definition of amount of states per energy interval, which will work only if you have like 1,000 orbitals. If it is less than 1,000 orbitals, DOS composed from DOS-CAR will look very ugly. It will have sharp edges and more gaps. So it is good for big systems, but will not work for small test systems. Make sense?
Got it. Thank you.
Great. Yeah, thank you. Are there more questions to Venjan? Questions 1, questions 2, questions 3. Please join me thanking Venjan.
Thank you.
Venjan, you can stop sharing. And the next presenter, to my knowledge, is Haley. So Haley, would you like to share a screen? And thank you for sharing camera. So little introduction. After we got basic skills of how to run VASP and how to analyze output, we may want to modify not only chemical structure of bonding, but also configurations. How does the model respond to adding or removing charge, to flipping electrons, to perturbing by light? And this is when we go from blind running of a software to versatile usage of the software as a true scientist. And Haley will open the door in this direction by teaching us about anions and cations. Okay, Haley, floor is yours.
Thank you. Yeah, I'm going to be talking about modified electronic configurations, more specifically how to make cations and anions. So here's the titanium-based complex we've been working on in class. And in order to change the charge on your molecule, you add this line N-elect into your INCAR file. The neutral number of electrons in this molecule is 32. So to make it a cation, I change the number of electrons to 30. And I've plotted the density of states for this molecule as well. You can see that in the valence band, that top state is not fully occupied now. And so here is the states and the states and the occupations. And we can see that the lowest unoccupied orbital is number 17 and the highest occupied is 16. I did the same with the longest oligomer molecule that we were looking at. Here I did 162 electrons as the cation and plotted the density of states for this as well. And the states here, you can note the lowest unoccupied state is 82 and the highest occupied is 81. And I've done this for all of them so we can compare them at the end. Then for anions, it's the same thing, except for here you'll add electrons. So here's the titanium complex with 34 electrons, and you can see some of the electron densities now in the conduction band of the density of states. And here are the states for that one. You can see 18 is now the lowest unoccupied state. And for the longest oligomer as well, here I have 166 electrons, and the same thing is apparent in the density of states here. And the lowest unoccupied state goes up to number 84 now. So if we compare the density of states for the neutral molecule, the cation, and the anion, what we can see is that compared to the neutral, the cation has the top state with less electron density in it, and the anion shows electron density present in the conduction band. And that's seen as well in the density of states for the oligomers. And that's it.
Okay, please join me in thanking Haley. I'm trying to clap as loud as I can. The presentation is open for discussion. Let's check. Are there any typed questions in the chat line, or anyone wants to raise voice and express either concerns or admiration, or maybe ask practical questions? Okay, I will ask questions and give extra credit to myself. So in slide, I don't know, 3 or 4, you did demonstrate partial occupation of orbitals, where orbitals were neither 2 electrons nor 0, so something in between. It looks natural because of the degeneracy of the orbitals 15 and 16. But do you see any, as a practitioner of computational chemistry, do you see any way to remove this degeneracy if it irritates someone? Are there any practical steps that will naturally remove this degeneracy and double occupancy? It's not an exam questions. It's more invitation to share crazy ideas.
Would heating the system change that?
Okay, I like the answer. Heating would probably increase this mixture and will make it very partial. So opposite, cooling may help, but if it is 0 Kelvin, maybe not. But I like the direction of your thought, because the distribution of the Fermi energy depends on the temperature. Yes, Fermi distribution. Any other ideas? Did you optimize this structure with these keys, or you used NSW equals 0?
I'm not sure.
So in the in-car, we can either do single point. Yeah, you see NSW equals 0 in the line 1. Let me count it here. 1, 2, 3, 4, 5, 6, 7, 8. Right? So it means that we take the snapshot of initial geometry. But if one would put like 100, the geometry will, the forces in the charged system are different than in neutral system. And the forces between atoms will bring to new equilibrium position. And often this trick will make electronic structure more healthy, and it will remove degeneracy. So it is one trick. And another, if one would use, instead of changing number of electrons, one can alternatively use Fermi key for repopulating orbitals that I hope Adam will present tomorrow. And there one intentionally puts certain number of electrons per each orbital, whether WASP agrees or disagrees with that. Okay. More questions. At which circumstances, which research circumstances one would need the modifications that you did report? When do we need to study anions and cations?
If the system that you're interested in is cationic or anionic.
But like in which situations systems are coming into anionic or cationic forms? Just from your chemical intuition.
I'm not sure I understand.
For example, okay, let me, I'm giving question and answer. If you are studying electrocatalysis, like if you want to model electrochemistry, when a molecule approaches the electrode and getting a charge, when the molecule is getting oxidized or reduced, would you agree that a molecule is transferred into either anion or cation based on which electrode it approaches?
Okay.
Okay, good. Thank you for approving. And last question, maybe it's too many questions, but I'm really curious. How does injection of a charge or making anion and cation changes conductivity of a material?
So I think that if you reduce the number of electrons, this increases the band gap, making it more insulator-like. Is this correct?
Yes. So good. And if injection charge decreases gap, then
increasing the number of electrons would decrease the gap, making it more metallic-like.
Okay. Yeah. Yeah. Thank you. Thank you. I like the answer. Okay. Last chance to ask questions to Haley in this session. Questions 1. Questions 2, question 3. Let's please join me in thanking Haley once again. So the next presenter, to my understanding, is Lola. So Lola, would you like to share your screen?
Yeah.
Okay. And yeah, maybe once again. And a little introduction. Haley was teaching us how to change charge on a system. And Lola will teach us how to change multiplicity, which is, and maybe she will explain in which circumstances it is needed. Okay, Lola, floor is yours.
Okay. Good evening, everyone. I was speaking about unrestricted DFT. So a quick one, according to the rules, the Hund rules of maximum multiplicity, which is applicable to like open shell configuration. The rule sort of like states that given electron configuration, the lowest energy term is assigned to the one with the greatest value of spin multiplicity. So orbitals with equal energy will fill singly first. Like in this case, you fill it singly first instead of pairing it up. So, what exactly is spin multiplicity? It's a way of quantifying unpaired electron spin, and it's defined by 2s plus 1. Spin is a type of angular momentum where like the particles move around as a result of angular momentum instead of linear momentum that we learned about in high school. So electron has an inherent spin. It's and the spin has magnitude, and it can be measured with a value, say n. And the spin can come in different states. It can be spin up, it can be spin down. The n in this case can either be integer or half integer. It can take any of these values. So electron is said to have half integer spin. And here I'm just showing an example of like the case of oxidation. So you have copper with this electronic configuration, and it undergoes oxidation and like carries 3+ charge. 3+ charge would have 8 electrons in the d orbital instead of 10. And this is exactly how you would fill up the energy levels. Instead of putting these 2 into 1, you would do 1 first and then the next one second. And so because you have, this is a half integer spin, and since you have 2 of it, 2 times half will be 1. So when you put 1 into this formula, you get 3. So copper 3+ will usually exist in triplet multiplicity. And so when your spin is 0, the multiplicity will be 1. For half spin, it will be a doublet, and for spin 1, it will be triplet. So how exactly does VASP implement this? You have to specify the spin using the iSpin tag. When you include iSpin equals 2 in your NCAR file, you are telling it to do like the spin polarized calculation. And for the case of multiplicity, it uses the tag n up down, and it's the difference between the number of electrons in the up and down component. So I'm just showing the picture from the previous slide. you have two up components here, but you don't have any down components. So this would be 2 minus 0, and you would usually just put n up equals 2 if you were to run calculation for this particular system. When you specify n up down equals 0, it will be singlets. When it's 1, it's doublet, and when it's 2, it will usually be triplets. So here I'm looking into one of my files where I'm looking at the in-car. And if you look here, you see I spin equals 2 to show spin polarized calculation, and then up down equals 2 to show triplet multiplicity. Now I'm trying to compare the energies of two different structures for when you specify spin or not. This is the energy that I got when I specified that I wanted to do spin polarized calculation. So this time I'm going to check another file of mine, which is not spin polarized. I just want to look at the effect on the energies. So looking at the in-car file here, if you look through, you would not see any I spin or any n up down tag here because I am not doing spin polarized calculation. So if you look at the energy that I got here, compared to the energy previously, the one with the spin polarized calculation is lower compared to the one without spin. So here I'm putting the energies of the two different situations where there's spin and when there's no spin. And typically this is what it looks like. So when it got this value, this is what it was trying to do. But when it was getting this value, this is what it was trying to do. It was trying to fix this into one energy level. And this is what you call the unrestricted. And this is the one that you call restricted. That's all. Thank you.
Okay, please join me thanking Lola. I clap as strong as I can. And it is very important instruction and general background because some of us will need spin polarized calculations for our project. So any questions you wanted to learn from Lola how to run these calculations, or you want to challenge her with questions about background, please speak up or type the question. While it is going on, let me ask a couple of questions to Lola myself. So Lola, you did, okay, let's start from this slide that you're showing right now. So you're showing a diagram where your each electronic level does have either 0, 1, or 2 electrons, right? Please confirm that we are on the same page.
You say 0 or 1 electrons. I didn't get that.
You're showing schematic diagram, right?
Mm-hmm.
Do you see what I'm showing, or you're not?
Yeah, I see.
So in your unrestricted, you have orbitals filled with 1 electron up, or 2 electrons up and down. And in what you call refer to as restricted, you have orbital with 0 electrons, and other orbitals are filled with 2 electrons.
Yes.
So do we see any confirmation of this picture in the outcar file? What should I do if I want to explore certain orbital and tell whether it has 0, 1, or 2 electrons?
The outcar file,
yes.
You will have to spin in the outcar file, you will have two spin component sections, one that says spin component 1 and another one that says spin component 2, which shows different orbitals and different energies. Okay, so on this slide, one should also show the list of orbitals and their occupations, right? Yes. Okay, yeah, thank you. If I'm happy, if anyone wants more questions, ask to directly. Then at the very beginning, you did mention a rule of maximal multiplicity, right? Yeah. So would you please, not all of us have chemical background. So can you tell a little bit more? Like, for example, one can be confused. If the
ion, the atom, has, let's say, 22 electrons, as in titanium, can we get 22 unpaired electrons?
No, you can't get 22 unpaired electrons.
Huh? You
can't get 22 unpaired electrons.
Why? Just explain how the principle of maximal multiplicity works. Does it make all electrons unpaired, or is there any restriction?
I mean, it depends on the system you're working with. Some will be paired, some will be unpaired.
But so, which will be paired, which will be unpaired?
The ones in the SP will most likely be paired, but like when you are going after, like S will definitely be paired.
Okay.
Depending on the system that you're working on. If you're having something like nitrogen has the S will be paired, but like the P will be unpaired.
Okay. So you're telling that d electrons, transition metals, they have up to 10 electrons. And what is the maximal number of unpaired electrons for any transition metal? Like, can there be 6 unpaired electrons?
No, there can only be 5 unpaired electrons.
So why 5? How? Because please explain it to those of us who do not have chemistry background. So why maximal number of unpaired d electrons is 5?
Because first of all, d orbital can only take what's it called? Can only take 10 electrons, and hold on. Okay, d orbital can only take 10 electrons, and just like how in the P, can you see my screen? I'm trying to write something.
Yes.
Okay, just like with P orbitals, we have Px, Py, and Pz. Okay. But for d orbitals, what you have is dx squared, y squared. You have dx, dz squared. You have dxy. And you have dyz. And then you have the xz.
Okay.
So
okay.
This is 1, 2, 3, 4, 5, and they can all take 2 electrons individually. So if it will ever be unpaired, it can only be 5 unpaired electrons.
Okay. Yes, I'm very happy. And last little question. Addition to this question, what is different in each of this dx squared minus y squared and so forth? Which quantum number is different for each of these orbitals?
I don't remember the name, the quantum number that is different, but I know what's different about them is the orientation of the
like SPDF, it is total angular momentum. And then there is, in addition to total angular momentum, there is, like if you in hydrogen atom, you have 4 quantum numbers. Haley suggests spin angular momentum. Can we say Z projection? Projection of angular momentum? Okay, yeah, thank you. So,
yes.
Okay. Last chance to, I'm happy. Last chance to ask questions to Lola by anyone. Questions 1, questions 2, questions 3. Please join me thanking Lola once again. Lola, you're welcome to stop sharing. And I believe the next presenter is Amir. Amir, would you like to share screen?
Can you see my screen now?
I believe I can.
Okay, sounds good. All right. So hello everyone, this is Amir, and today I'm going to talk about the density of states images for doublet and triplet. So first of all, what is doublet and triplet? So here's an example of a singlet, doublet, and triplet. So a singlet state refers to a system which all electrons are paired, so we have no unpaired electron. In doublet, we have one unpaired electron, and in triplet, we have two unpaired electrons. And then in order to do the calculations for the DOS of this doublet and triplet, in the in-car file, we have to specify the n up down here, as Lola just talked about. So if you put it to 0, it means you're talking about singlet. If you put it 1, means doublet, and 2 means triplet. And here the calculations are for the titanium hydroxide, which you can see this right here. And so if you submit your job using SPatch debug.sh, you can get the outcar file. And then in the outcar file, you will see two spin components, spin component 1 and 2. So in this case, which is a triplet, you can see that we have two unpaired electrons, which are number 17 and 18 in the spin component 1. And I think I've admitted payment. And then, so yeah, in the states down, we have number 16, which is 0. So there's no electron in with state down. And okay. So we have to copy these spin components into two different files named states up and states down. And then we're gonna call this, and then you have to grab the Fermi information from the outcar file. And then you call the script, and then you put these information, you call the dress DOS up script, and then you put this information that you got from the previous step in here, and you do the same for DOS down, and then you can plot it with the GNU plot, and then this is how it looks like. Then you can download it from, actually you have to first of all convert it to the PDF format, and then you can download it to Photon, and then from there you download it to the local computer, and you can see this, the DOS for triplet. And then here for the doublet, I have two examples. One of them is a cation, and another one is an anion. So the cation format is formed with the titanium hydroxide. So in the in-car file, I've changed the number of electrons to 31, where 32 was a neutral. So we have a positive charge here, and then that will essentially make it a doublet. So you put the I spin equals to 2 so that you can have these, oh, sorry, yes. Yeah, so you put the I spin equals to 2 and the number of up down equals to 1, because you want to calculate the doublet. So this is how the states confirmation looks like. So as we have a doublet, we have one unpaired electron. So you can see the number 16 here is 0 in the states down, whereas in states up, we have electron number 15 and 16 equals to 1, which means that there is an electron right there. And you follow the same steps for calculating the triplet. And this is how the DOS looks like for a cation. And for the anion, we've used the vanadium hydroxide system. So instead of titanium, we've put vanadium, which has one more electron than titanium. So this is how the states up and down look like. So electron number 17 is 1 here, and in this one, this states down. Electron number 17 is 0. And this is how the DOS for this anion looks like. And if you have any questions, feel free to ask.
Okay, please join me in thanking Amir. It's really useful and nicely formulated talk. So anyone in the online audience is welcome to type the question or raise up the voice. So Amir, I do have a couple of questions, and anyone is welcome to stop me, not just stop me forever, but give an alternative question. So can we go a couple of slides back? I'll tell you when to stop. Yeah, this is enough. Here? Yeah, this one. So if we draw a line on the x-axis for the conduction band for unoccupied electrons, it looks like your green and yellow line do have a mirror symmetry, right? Those with electrons up and those with electron down are the same or almost the same. And when we look in the occupied orbitals, this symmetry is broken. So orbitals up and orbitals down, those up and those down do differ. So why? How to understand it? Just how do you interpret this picture? What is wrong? If we believe that there are same orbitals which are either occupied and unoccupied, why we see this shift of energies? Just any comments? It is not a exam question. It's not a provocation. Just share your analysis.
Sure. Is that because we made a cation here?
Okay.
And because I remember that you said it is going to be more realistic if we do it with anion rather than cation. So it's not like we force this system to be like that and then just it changed those conformations there.
Okay. I am going to throw in an idea, but I'm not signing under it. It's only a direction of thought. So do not take it as correct. What if we have more electrons in the spin down, they repel each other and therefore they add additional splitting, or if there are less. So repopulating orbitals add additional interactions and it affects electrons only of a certain symmetry. Would it make sense?
Yes.
Okay, and the major freedom that WASP gives us and this unrestricted spin calculations, that orbitals with the same number, so I think it is your orbital 16 with spin alpha and spin beta, do have different energies. So it is not a one orbital that can be populated with spin up or spin down. It is different orbitals. Set of orbitals for spin up and set of orbitals for spin down have different populations and different energies. Okay. Yeah, thank you for thinking about it. And I have a second question. Again, it's not an exam, it's not a provocation, just share analysis in which circumstances your skill of plotting spin polarized orbitals for doublets and triplets can help to the research. So which research objects would benefit from this skill? How do you imagine, what should you study in that, which study would make you to plot such images for research?
I think, is that the case when we are like thinking about the interaction between molecules, like the conduction band, when that is important for us, or maybe the radicals where we are—
Radicals, yes, radicals is a really great answer.
Yeah.
And which object you are looking at right now? Just describe it by lay words. You were showing the structure, but explain which molecule do you describe in this example?
I think this is the titanium hydroxide, I guess.
Yes, so it is a metal ion surrounded by some organic ligands or inorganic ligands. So in chemistry, it is often called as metal organic complex. So if you want to study any metal organic complex, you will definitely need this skill. Okay, more questions to Amir? More questions one, more questions two, more questions three. Let's thank Amir once again. Amir, you are welcome to, yeah, thank you for stopping the share. And the last but not least is presentation by Anand Gupta. So Anand, would you start sharing? So
yeah, thank you.
This subject is listed the very last in our list of subjects, but it is something that I promise everyone will use. So it is exploring how systems are changing their structure, at least interatomic distances and at most electronic structure, if we bring in realistic temperature. And Anand will cover 1/3 of this question, basically how to analyze pre-computed molecular dynamics trajectories. Okay, Anand, floor is yours.
Yeah, thank you. Yeah, I'm going to present on practical steps to publish a movie based on molecular dynamics. Yeah. What is a movie? It is a combination of different images. So VMD takes a snapshot equivalent to the frames. So it creates different snapshots of a frame and combine these images to a video using the process tool. In our case, it is Video Mac that convert images into video. Now I'm going to show the practical steps how to convert these images to the video. So after creating the XYZ file, just drag and drop at your PC. So even using the XYZ file, you can use any kind of file like your outcar, incar, or concar. I actually in my presentation I used three files: XYZ, concar, and one more I used PDP from the PDB database, and that is a Crambin protein. Okay, so using after drag and drop, you can just go to the VMD main interface. Then you have to load new molecule. So new molecule, then just select from your directory. Then it is XYZ, then load.
Hello, hello. I think there is a little connection interruption. Anand, can you hear us? Do we have the rest of the, is the rest of the class hears Anand?
No, we can't hear.
Oh, we don't hear him.
No, we can't hear him.
Just please type in the chat line or that Anand may want to switch on and off microphone, and if it doesn't work, just do something. Anand, can you speak? Can we hear you?
I think his connection is interrupted because
he's not in the chat line.
Okay. So we need to, if anyone has his email, just email him that he needs to rejoin. And I have an idea. Let's just go over his slides because we need to have this material presented. So if Anand will show up, he will continue presenting his story. But if not, I will just open his slides and maybe I cannot explain it in such a nice way as Anand was. Anand, did you reconnect it?
I think he's having some problem.
Huh. No, he's
Dr.
not.
Yes, his computer is taking some updates. That's why.
Oh, okay. Let me just show his slides, and then he will maybe try to present them other day, but now we need to deliver his slides to the group so that we do not have interruption in the class material, because it's not only midterm, but also the skills. So I'll just replace him and present his slides. So let's go here. So what he's showing, that he needs to recognize the type of the file, and if it is XYZ, one selects just XYZ. What he shows here, x.car, would work if he would read x.car, download x.car from the VASP. And upon loading, the molecule is showing up here, and the goal of his slide, of his presentation, was to show how to make movies. So I believe in the next slide he's showing how to make it, make the molecule nicer, to replace this thin lines with thicker lines. Okay, Anand, can you share your screen? Is your update is done?
Yeah, it was. I don't know what happened, but really sorry.
No, not a problem. It happens with technology. So maybe when we will have the final exam presentations, maybe the best thing is if we all come into the same room, and it will avoid technical problems. But whatever works.
No,
please share screen and keep going.
Yeah. Okay. Okay. So after loading your molecule, so it is having different kinds of sets you can upload in any format. Like you can see here, there are postcar, outcar. I am using, as I told you, I am using 3 types: XYZ, then concar, and one more is from PDP database. So, okay. So now I have uploaded. So this is the interface. So you can see here. So I have to just, it is now loaded. Now the next you have to, you can see here, it is not very good picture. So you can go to the representation, graphics, and representation. So after that, you have to select the dynamic bonds, and then you have to, whatever you want to do, like transparent, and there are other options are there. Then you can select here the sphere resolution, bond radius, and bond resolution. And if you are working on any organic molecule, so this sphere resolution, there are different sets of resolution for sphere and bonds radius. So after that I selected, then I go to the movie maker, then you have to select the in the movie settings trajectory. And if you want to keep that files, but I don't think anyone want to keep that big file, so delete, that is a auto option, delete images file after creating the movie. Okay, now you are set to create your movie. So you have to set your working directory. So after that, you just make movie. So it will create the different sets of snapshots of any molecule. So now you have to give the path of video Mac. So would you like to continue? Yeah, yes. So after giving the path, as in my computer, it is in the C. So I given the path, then start, then now you are done. So these are the 3 movies I created. Just I want to show. This is the from using the XYZ. So this is the first movie what I created, and the second one is Olig 32 molecule. So which I created by using that concar file. And the third one I used, that is a crambin protein, which is a seed protein. I just want to see the difference between the organic and inorganic molecule. So this is the movie of that organic molecule. So this is all about to create a movie. Yeah. Thank you.
Okay, please join me in thanking Anand. So are there any, I know we have a few minutes over time, but are there any questions or criticisms towards what Anand has presented? So Anand, please share your slides once again, go to last slide.
The last slide?
Yeah, the last slide. So I do not see questions from the audience, but I'll ask myself. So, no, yeah, this one. The first movies that you're showing is really helpful. It shows, can you run it once again?
Yeah.
So it shows how positions of atoms are changing during the dynamics. And you are telling that one should select the trajectory in the settings. In the others, I do not see interatomic distances changing. So if you use CONTCAR, it has only one snapshot and it will not show movie. So one needs to use either movie.xyz or x.car as an outcar from WASP. So here it is not actual. It's not movie of molecular dynamics. It's just three-dimensional representation of a molecule, which is helpful, but it doesn't tell us main question how the molecule behaves upon heating.
Yeah.
Make sense?
Yeah. Yeah.
So those movie number 2 and number 3 are just pleasant decorations, and movie number 1 is really helpful scientifically. So the question which you do not need to know the answer. It's a question to everyone. What if we need to monitor a specific bond? Is there a way to extract interatomic distance at each time step during the dynamics? Can VMD help it?
Definitely, VMD can help it. We can change the different bond, like resolution and different.
No. Yeah. The numbers, how long is the bond? Is there a way to measure the distance at each step of the trajectory?
Yes, we can do that.
Yeah. So Hemant, just tell a little bit more.
So for that, we need to select the bond from the labels, and where we can select two residues or two atoms from the screen, and then it will automatically visualize the bond. And so once we run this particular simulation, that particular bond will change its distances based on the simulation. And if you want to frame it, once again we will go to that label thing, and where we can plot the bond, or we will get the data for it based on the frames. So
excellent. Many thanks. Are you presenting tomorrow, right?
Yes.
Would you please add maybe one slide on this additional skill, how to measure distance change along the trajectory?
Okay.
So it will help the rest of the class.
Okay.
Okay. Let me please join me in thanking Anand for presentation, Hanmant for help with answering questions, and all presenters and participants to the discussion. So it went really successful. Many thanks to all of you. Meeting is done. I hope to share the recordings at least by midnight, and anyone who has free schedule tomorrow at 11 are welcome to join the session number 2, where we will have focus on absorption spectra